Okay, so here's where I wish I had a whiteboard for all the graphs. Okay, so all of these things may be together. I'm not going to draw the non-positive suction required head. Why? Because it's usually so low down here, you're usually going to satisfy it. Really tight systems or large systems could behave that way, right? But for your project like that, you really just need to think about these idea of curves. So here was the pump curve, okay? And then let's say here, here's the H naught, right? Here's that constant term in front of the system curve that it's going to begin at, right? So let's draw maybe one of them. So this is the first system we have. Here's the pump. Okay. So here's just system 1, right? That's associated with it some total resistance 1 value. Okay, so my first design system, I have just a total fluid resistance. I did an Excel chart calculations in to get what that value is. Plot it, looks like this. Okay, so here is one operating point that we have. Got my pump that I bought, has a characteristic curve. I have system curve, intersection point right here. It's an operating point. That's what you want to operate at, okay? So how do we change this? You have 2 ways to really change where this operating point is. You could lower or raise this initial, this initial head here, right? If I just take the exact same curve, so think of these as parallel, right? Here's sys 2. It has the exact same, this is K total 1. It has the exact same fluid resistance. All I've done is changed here. Look what I did. I changed the operating point because I've moved it inward. So raising initial head, right, lowers operating flow rate. Lowering it, same idea, you'd put it here. So lowering initial head raises operating point. I've gone further in the positive direction for this. So that's just this way. And this is usually not feasible. Right? Usually you can't change this value because it's elevation or just the requirements of the pressures and velocities are too strict. So I don't see many problems where you can change that, but as an engineer, it's still in your tool bucket, right? You can still change this to move this thing reasonably. But more commonly, one way to tweak it is actually to tweak this thing. And we did all those functional relationships to see how you could tweak it, diameters, lengths, friction factors is not much. I mean, clearly you could do these derivatives and show yourself, but that's the idea. So what do you get? So I'm going to draw a tangent right here just to kind of show have to operate really above here. Let me get rid of this curve because it's not really something we can do. So the other thing I could have sys 3. This is the third system operation, right? And this has some K total 3, right? Same thing. Okay, so, right, I've changed now only the resistance terms based on flow pipe dimension parameters, and you can change the curvature of your system plot, right? So if I make this much, much smaller than my original system design, I'm going to flatten out the curve, right? Flattening the curve out, make this 3. Flattening this curve draws the operating point forward, makes the operating flow rate more. Right? Likewise, I could do this term, right? This one right here, well, this is actually much, much greater, much, much steeper polynomial curve, right? This time around. And what did that do? That made me go here. and this will be 4. So really, really big flow resistance terms right there. Draw this curve, make it more curvy, make it curl upward, and that's drawing this operating point closer in. So so increasing the resistance here, right, draws your operating point flow lower. And those are important to look at. Anything else? So sort of, I guess, in summary, right? So this is increasing the K total of the whole thing. You're just curling that system curve up, right? Because this was a quadratic polynomial in your system design. Okay. So, right, you can see with systems, right, you can move this flow rate around. I gave you 2 ways to actually do that, and there's another design way of multiple pumps. But let's just, right, you get a sense that actually you can shift this operating around. And then also remember that this pump itself, right, the pump itself that you bought came with an efficiency, right, an efficiency plot similar, and that identifies, right, a Q, right, a best operating efficiency point. So the efficiency graph intersects with the pump curve, giving you a best efficiency point, and then the system curve also intersects the pump characteristic curve, giving you an operating point, right? And you want these to be close somehow. So you can change maybe designs on here, draw this forward, curl it up, curl it back. This could even be choosing different, right? I could just choose different pumps with different BEPs, looking at tables to get that close to my operating point for my system. Say you couldn't actually change anything about the system, right? It's too expensive. Well, that comes to, right then you'd be looking at like, okay, well let me get my pump that gets these 2 things like close, because these 2 things close means money savings, right? Because you're not wasting a bunch of power going into unused power transfer into your fluid. 7. Okay, let's go through. So now, the other tool you have then is to look at multiple pumps in series and or in parallel. That also changes how these graphs intersect, right? It's all about the intersection points of these pump curves, right? It's all about where the intersection point is. An intersection point defines a flow rate, which is a requirement usually, right? I need this much water per day, etc. So that's the language of these pump curves. So we have 2 ways to do it. You can do series pumps. Okay, so here's one. Let's say my system curves like this. Okay. So this is just, let's say, P1. So this is just a simple addition of both of these pumps in a row. So what this looks like is series pumps. What they do is they actually add the pump curves themselves. Say they were identical pumps. So this is actually just P1. What you would do is you would just add the 2 pump curves together like that. If they were different curves, you actually can figure out approximately how it works, right? In the ideal case, you can actually do it for a centrifugal pump, right? So in the ideal case, if I had H1, right, the ideal pump, I would have like a U squared. This is G. And then here I have U and then coating. Remember this formula? B Q, it's a linear one. Let's say it's a different angle even, right? You can see that we just add these. Okay, so summing these 2 things, what you're doing is you sum the 0, right? You sum the y-intercept and then you sum the slopes. So you could actually make it steeper right, you could actually change the actual slope of your ideal performance curve as well. So it wouldn't just be two parallel lines. If they were different pumps, you could see how this slope, right, the addition of both these terms, right, could make something more, right, could make something more steep or less, right, it's definitely steeper, right? The idea being adding two pumps in the ideal case gives you a sense of how they add because, right, if I just have this line right here, this is just for pump one. If I added two of them, I raise the 0 point, and also I can make it a bit steeper as well. That's a little exaggerated, right? Because this is this expression is right. This U2 B pi. Where the primes are, well, my primes here are just like the other pump, so it's two negatives, right? So this is more, this could be more steeper. That's all I'm trying to get at when it comes to adding them. It's not, oh, then these lines don't have to be parallel. You can just easily see what this value is, and then you can get what the slope is. And again, in reality, recall that when you're adding them, what's happening is there's an actual pump that's looking like that. Okay, so pumps in series are helpful because if you can't change the K that much, if you don't have a way to change that K value, if you don't have a way to change that, right, that delta Z value, you can still use series pumps because what they're doing is what, right? They're going to help you. Say I have a pretty steep system curve, okay? Right, steep system curve like that, and pumps I buy look like this. Here's my operating point there. So this is garbage. It's garbage because it's just usually too low, right? I mean, your intersection point is just horrible, right? But you want to get this kind of further out to a requirement, right? Well, series can help, right? Let's say I put 3 of them in series and I can really bump this up. Good. So this is getting better, actually, right? You're getting closer to where you're, right? You're getting closer to some sort of like requirement flow rate. And then you're seeing this, right? And then this sort of head rises there. So that's the idea of what series pumps can help you. So series is good for steep. Right? So series pumps are good for steep system curves. Steep system curves, right? What does steep mean? Large resistance values in your pipe. So those are fuel systems, right? Systems with very tiny pipes, intricate turns, lots of minors and Ks, and very tumultuous path that fluid has to go through. You're gonna get very steep systems. What else do we have for looking at our pumps? We have the parallel case on how these things will look like. So parallel is slightly different because what it does is boom, boom. In the parallel case, since the head's conserved, right, you can't raise this value because at 0, they would all have to have equivalent heads in the parallel, right, in this idea of the parallel circuit. But what it can do if you add them, so we'll do this. So 1 curve, 1 pump, 2 pump, 3 pump, right? It's drawing out the pump performance curve while keeping this value the exact same. Okay, so right, it's kind of the same thing, right? Here's this Q right there. Add more pumps in parallel, and what you're doing is you're drawing that. These aren't derivatives, they're just primes for a different operating point, but that's what you're doing. The more parallel pumps you have, the more flow rate you can get for your pump requirements, right? So the whole point of parallel pump things is for flat system curves. right? Parallel pumps. And what does flat mean? Low, small k total values. So, right, for that city water types, I think this stuff is just negligible as all hell, right? In reality, you just kind of have a flat line. So, in order to get like an operating point you really want, cities have lots of parallel pumps that work, right? Or parallel turbines. Like what's a hydroelectric dam besides a bunch of turbines in parallel to get power out of the water? Because you have this giant. All right, so that's sort of like the rules of what you're trying to do, of ways you can change these plots around. You can change the Ks, you can change, let's say, maybe change the initial head on your system, and then you can also put them in series and or in parallel. But the series and parallel, you can kind of say they're restricted to just a couple things, where series are for steep systems, parallel are for shallow, flat systems. Another thing kind of talks about how maybe it all comes together. But right, so that's sort of the end of where we are right now on this pump stuff. I've drawn you all the graphs, right? And you get these graphs, and then from those graphs you look at intersections and you can calculate things based off that. Okay, so for a pump selection, right? There's a good process, right? Or it's given, right? What's the system resistance? So then you can plot, right? This is the pump, right? So this is the system curve. Right? Other kind of step you have to do is, right, you have to make sure usually this is satisfied. Sometimes in homework problems it's not. I can't really find when this is like really an issue, because sometimes cavitation will just occur, unfortunately. So that's just one thing to make sure in your design, though, is you have to go along at each pump point and make sure that this is going to be true for the fluid on each intersection point. Okay, and then you need to get you need to obtain this somehow. In all of the book problems you have, they actually like give you a plot for efficiency or tell you how this works. But that leaves out part of the story of you as an engineer going, well, what's the efficiency of the pump, right? That's important, right? That's critical. So you have to kind of put that in your toolbox of like, okay, I have a pump. How efficient is it? Can you measure the efficiency? Give me that graph. Okay, and that helps you get this BEP. What else do we have? So you have this plots the system curve. This gives you the, right, so this gives you the QBEP, and it gets you, right, and it actually gets you this pump curve, this step. So this step right here is obtaining this pump Q curve because you're selecting a pump that has a pump performance. If you were designing the pump, you would start with the ideal case, right? If you're designing a pump, you just have this HI. That's the lecture we did before. That was a linear, totally wrong approximation. But it can get you on the right track on this selection idea. So then there's that. Then, really, plot them. I'm out of order, right? So then plot them all. Plot them all and think. That's important, right? And then the goal. So I would sort of summarize this as the whole goal is, I want to minimize this for all variables you can change. This is just a classic optimization thing where if I take a difference and square it's always possible. So it makes it a coercive function, was what they say, or has properties that can be optimized. So don't worry. But the idea is really the goal then is then to use parameters and use in engineering intuition and use anything at your availability to maybe get these things close together. because you want your operating point to be close to your best efficiency point on the pump, because if it's not, well, you will be operating at the right, your operating point would be good, but you'd be wasting a bunch of power. Wasting power means wasting money, so you don't want that. So if you're an engineer and you can actually do this and say like, hey, I got you the best one because I minimized this function right here. No one's going to know what you're talking about. It's going to like, what's the math? What's optimization? But if they did, they go like, kudos. Real cool. Thanks for saving me cash with minimization, optimization, and actual math. But, it doesn't have to be mathematical optimization, right? You can just case-by-case check and rank these things in a discrete setting. And that's what normally people working are going to do. They're not going to run an optimization algorithm to do this. They're just going to make a list in their head maybe on like var. You can just make some ranking on all your options that you could do. Because you can't usually continuously change a system, right? But given a bunch of tables, you could actually like rank all of these cost penalties. So big thing is using your imagination. So all these things just are involved with that, man. And it's, in terms of the math, right? Again, I think it is going to, you have some curve like that, and you have some curve like that. And this is the first thing you're after for, right? So that involves a system curve and a pump curve. So how do you get that? Well, I think everyone can mathematically appreciate how to, set things equal. You need to take the actual pump curve, which is a function of Q. This is the thing you're solving. Well, at Q naught, I'm equal to They're just setting two equations equal to each other, right? This one you actually have the form of. So this is okay. There's even a Q in there because of the friction factor, but I actually think I actually just use the same friction factor for all of them because it's not as sensitive to other parameters. But again, you can just get this. And then this is the actual pump curve. It looks like this, right? So, right, you could, it could look also like a quadratic, but usually they don't. I mean, we had a line, right? The idea is, right, sort of the biggest thing is you could have another sort of initial, right, some 0 point head, and then it's going to be a minus a. If you model like a quadratic equation, right, then this would be a negative sign because it's going down. So this would be some, like, let's say, I don't want to, alpha. This is not what all actual pump curves look like. You could approximate them, but sometimes they look like lines. Sometimes they look like a half a logarithm function, right? But sometimes they could have it could be like a negative to the 5th power in there if you fit it all right? But if you have data, you could turn to something like this, and then with that, you could actually solve where this is. So that's just one idea. So that's how that's the idea of figuring out what your operating point is instead of just looking at it mathematically. But, right, it's mathematically, if you just plot them, you can just take your finger and go down, and then that's your operating point. So let's say it again, right? You can do this stuff with the math if you had all of these sort of systems right there, right? If you had this K and all that stuff, or if you had a bunch of data for your system and your pumps, you could plot them, take your finger, go down, and get your operating point, get your operating flow rate point. So maybe just sort of weigh those options for these things like that. Not saying, right, but the idea is sometimes the math helps to maybe give you a roadmap of how you should optimize. So I just put that up there for anyone that maybe wants to pose this second project mathematically. Okay, those are all the techniques I have for you on pump selection. Next, I'll go into comparing pumps, but from looking at it actually, there's nothing actually in project 2 that will involve the similarity stuff. I was just a choice on my part because I couldn't think up enough fake things. So, really from this one and the second one, those are all the tips that you have to make a bunch of plots and select a best pump. And just think about that minimization, and then that would get you closer to like involving the combustion part of the project description. But you got a bunch of plots to consider. Oops, someone's on Slack. Okay, so that concludes this lecture.